Cool. Okay. Hi, everyone. My name is Kobi, and I'm a PhD student in Alexi's group. So today I'm going to talk about machine learning for thermodynamic prediction. And just to start out, kind of the reason this is important is a lot of chemical processes and the way we simulate them are underpinned by thermodynamics. So in chemical engineering, that could be reactors or separations. But even if you think about things like drug discovery, where you're trying to partition between the blood, or understand partitioning across the blood-brain barrier, you need to have a good understanding of thermodynamics. And the challenge is that getting these values experimentally can be both time and labor intensive. So in the fluid phase sort of thermodynamics world, the way this is still done is the same way it was done 50 or 60 years ago, where you run an experiment at a specific temperature and pressure, then move to another temperature and pressure, wait for however many hours to reach equilibrium, take another measurement, and this can be really expensive to do. And that's just to get like curves like you see on the right-hand side. So there are three different sort of streams of work that have been going on for almost half a century to try to make predictive methods for thermodynamics. So the first is group contribution methods, and these were invented first in the 60s and 70s. And the basic idea is you fragment a molecule into different functional groups. And then there are databases of coefficients for those functional groups, which you can then put through an analytical equation to get a final predictive property, so like an activity coefficient, for example. And the nice thing is they're extremely fast. If you have a database which already has all the fragments in your molecule, they work perfectly. But as we've discovered, a lot of molecules that you're interested in actually don't have fragments measured. So this is a real challenge for these approaches. And second is quantum mechanics. So you can go run DFT calculations, and there have been specific packages developed for fluid phase thermodynamics. So for example, COSMOS is very widely used in the chemical engineering community. And it's great. It gives you pretty accurate predictions, plus or minus 0.5 log units often. But if you have a molecule that has not already been measured previously, where the quantum calculations have already been run, then you have this expensive quantum calculation that can take anywhere from hours to days to run. And so this is not really great for if you want to screen lots of molecules. So then finally there's machine learning, and this is a field that's been exploding in the last 1 or 2 years in thermodynamics. The basic idea is we can train on some amount of quantum mechanical or experimental data and train a model to predict some thermodynamic quantity. So for example, a lot of people have looked at activity coefficients. This is where I wrote some papers on. And you know, this is really great. It works quite well. Once you've trained the model, you can get predictions in milliseconds. But the challenges are twofold. First of all, you have to have a reasonable sized database. And as I talked about, the experiments are difficult to run, so our experimental databases are quite limited in this field. And second of all, and I want to sort of focus on this, is the thermodynamic consistency. This is something I think we didn't really start to recognize until about last year. People have started to think about this. So one sort of thing that's been around for a long time and understood in thermodynamics is that there are certain physical constraints that all thermodynamic quantities should obey. So one example is Gibbs-Duhem consistency. I haven't written down the equation here, but it's basically that the partial derivative of the activity coefficient with respect to composition should be 0 in a binary case. And if you look at the right-hand side, the plot on the right-hand side of this screen, you'll see that this is an example of a machine learning model predicting the activity coefficients. And the first plot looks reasonable, the curves look reasonable, but then if you look at the yellow curve, and it's kind of hard to see here, the Gibbs-Duhem consistency is not always 0. And so therefore, if you use these predicted thermodynamic quantities in a simulation, you'll actually get non-physical results. And so this can be a huge problem, and you need to think about like how to solve this. And there are a couple different solutions. One has been to directly integrate thermodynamic models into neural networks, for example. This is great for very simple systems, but it can be challenging if your thermodynamic model is more complicated. The other option is to include it as a physical constraint in your training, and there's a paper actually we just put on arXiv about that, but that's not what I'm going to talk about today. What I'll talk about is sort of an in-between solution, which is taking advantage of the equations of state that we already have. So there's lots of development over the last 50 years of equations of state that have been derived either empirically or from statistical mechanics. And one of the latter is the PC-SAFT equation. So is a physically informed, basically, equation of state that has physically meaningful parameters. And those parameters are not thermodynamically constrained. And so the interesting idea here is to basically say, okay, we can take our experimental data, run regression using what is basically automatic differentiation to find those unknown parameters from experimental data, and then train a machine learning model to predict those parameters. And so the advantage of that is we get the thermodynamic consistency of the equation of state, but also can take advantage of the machine learning to understand the relationship between a molecular structure and a parameter. And so this is the idea behind ML-SAFT. It's a two-part framework where we do the regression to thermodynamic data we have experimentally, and that's on the right-hand side of that slide. And then secondly, once we have those regressed parameters, we use a machine learning model to predict the parameters. So I'll talk a bit about sort of the approach we took, and I'll kind of note here, actually, given that we had to talk about automatic differentiation, that one thing this would be interesting here is to do it all the way, so go directly from thermodynamic parameters to molecular structures. We couldn't figure that out because we didn't know how to differentiate through the thermodynamic simulation. I think people have figured it out in the last month or so. So this is a field that's evolving very quickly. But I'll first talk about how we try to do the regression. So I tried this initially just basically putting all the data I had through a regression, and it failed terribly. And one reason for this is that not all the thermodynamic parameters of the equation of state can actually be identified from the data we have. So for example, one of these is the dipole moment. And if you try to identify this for any molecule just from vapor pressure and density data, which is what we're using, you can't really identify it. So instead what I did is I used a large database of dipole moments that were measured both experimentally and from quantum calculations, trained a 3D graph neural network to predict those, and then use that as the predicted dipole moment. And so that ended up working a lot better. And we could get sort of like you see on the right-hand side and the bottom, going from an initial guess that's based on an average of the whole database to a very good fit to experimental data. So this is the first part, is basically just doing a regression to experimental data. Then, and here's just an example of sort of the overall database. We could get from an initial guess, it's just kind of an average of what the parameters are across the whole database. We then get to something that's much more accurate once we do this regression. So that's the first part. We get data from experiments, and I'm kind of going quickly through this, but it's actually where we spend most of our time. And actually, I've run lots of these projects, and it's always where you spend most of your time. The machine learning is easy. So then we tried a bunch of different machine learning models, and I initially really was interested in looking at graph neural networks, and I'll kind of talk about that. But as just an experiment, I also tried some models that used fingerprints. So these are circular fingerprints that are derived from a sort of deterministic algorithm. And you can then get this vector that represents your molecule, and you can put it into any neural net or any machine learning architecture. So we tried random forest and feed-forward networks. But in terms of the graph neural networks, I've found message passing neural networks to work very well, and I'll just quickly explain how they work. So you start with a molecular structure, and you can treat that structure as a graph where the nodes are atoms and the edges are bonds. And so you describe each atom with a set of features. So these could be like the formal charge, the atom type, et cetera, and the bonds with also features such as whether it's a single or double bond. And then you propagate in each sort of step through the network features through the nearest neighbors, and you update the features of the nearest neighbor atoms through a nonlinearity. And so you basically start to pass information throughout the molecule, and what you get is a representation on each atom that's informed by the atoms and bonds around it. And once you take an average of all of those features, you end up with a fixed length vector that describes your molecule. And you can put that through a feed-forward network to predict your property. The nice thing is this is end-to-end differentiable, so you can go from your property back to the features for the molecule and the parameters that are being used through those nonlinearities. So you end up with the descriptor for your molecule that's best suited for the particular property you're trying to predict. And so that's the idea behind message passing neural networks. We tried both the sort of standard idea that I just described, but also an inverted version of it called the directed message passing neural network that basically inverts the idea. It says the nodes are the bonds and the atoms are the edges. And so one other thing that I found is really important with these type of projects is to think about how you evaluate the models. And so what I did here is I clustered all of our data, and I basically made sure that in the train, validation, and test splits, there's a balanced amount of molecules from each cluster. And the idea there is that if we have a much bigger cluster, and we just do a random split, we'll end up with basically all molecules from that cluster, maybe in our training or test set, and not really representing the other clusters. And so we might either get an over inflated performance or under inflated, or a decreased performance than what we actually should. So, okay, I ran this and I thought the neural networks would work really well, but what we ended up with is the random forest working quite well. And this has to do with really the size of our data set. If you looked earlier, the data set's about 1,000, which is very small if you think about machine learning, but surprisingly for these type of properties, this is actually, I think, the largest database that's been assembled for this problem. And this is for predicting the density and vapor pressure, so over different temperatures, basically. And what you can see is that the message passing neural network works quite well for predicting density, but not very well for vapor pressure. And so I started thinking about this and said, well, can we maybe do something to try to improve it? And one idea that's been tried a lot in this area is transfer learning. And the core idea is that we have some source domain task where that task has maybe more data and is easier to collect, but might not be as accurate. And then we can, there's multiple ways to do it, but the way we looked at is kind of freezing the model parameters and only training a part of the model on the experimental data. So specifically the way we implemented this is I generated predictions for vapor pressure and density, basically the experimental predictions from a quantum mechanical simulation, COSMOS, for about 3 times the number of molecules we had experimentally. And there was a very small subset of those that overlapped. So they were kind of different molecules. And subsequently, I ran that same regression procedure I discussed earlier to generate regressed parameters. And so then we trained the model on predicting those regressed parameters from the quantum mechanical simulations, fixed the message passing part, and only trained the feed-forward network on the experimental data. And what we found is that the error decreased by about 50%. So we were able to halve the error doing this transfer learning procedure. And so the message passing neural network is about the same as the random forest on vapor pressure predictions, and is also still the best on density. So this is really powerful, I think, in showing that we can use these quantum mechanical simulations, which we have access to, but as I mentioned earlier, are often expensive and difficult to run. We can run them once, get pre-training data, and then use that to help improve our predictions on a limited set of experimental data. And just one note here is it's interesting because these are correlation plots between the values for the small subset of molecules for which we have both experimental and DFT calculated values. You can see that the correlation is not 0, but it's not perfect. It's not nearly 1. And so this is interesting that basically, even though there's a nonlinear relationship between the two, we're still able to learn something from this pre-training data that's useful for the downstream experimental task. So I'll kind of just, these are a couple examples where you can see that the transfer learning model performs better than the other models in the sense of its values, predicted values for vapor pressure and density are much closer to experiments. This is an example where that's not really true, if I remember correctly. And that possibly, I don't know if that has to do with experimental error, because there's one case where that experiment is actually very close to the transfer learning value, so we don't know. These experiments are collected from large databases that come from papers, which you never actually know how the experiments were really run. So I want to stop here and just kind of conclude. There are a couple of things we learned here. So the first is just that basically the regression part is actually really hard. Understanding how we fit our thermodynamic models to experimental data in a large scale way that's automated is often actually the more difficult task for these problems. And I think there's so much to be done on how you integrate the machine learning and that part together so that you get better results. Because, for example, we're only using about 3% of the data that we have available because of the constraints we put on the regression. We were able to still despite that, generate what is the largest open source database for this problem, and then use machine learning to predict those regressed parameters and get reasonably good results for predicting vapor pressure and density. The nice thing is once we have those predicted parameters, we can actually predict a wide range of thermodynamic quantities, not just those two that we regressed to. And yeah, and transfer learning actually did work in this case. I've used it a lot and it hasn't always worked. So this is one of the cases where it really did improve the performance of our model. So if you want to read more about this, there's a publication, or there's a preprint up that has more details on like comparisons to other types of models in this field and how the machine learning fares compared to them, as well as the full data set, et cetera. So if you're interested in that, you can see that. I'll just quickly thank everyone I worked with, BASF in Germany, who sponsored a lot of this work, and some wonderful collaborators from RWTH Aachen in Germany as well. And thank you for your attention. And I'll put this back up if you want.